Eric Darling here with Darling Data, and today's super ultra, probably the most important video you'll watch over the next 10 minutes. We're going to talk about multi-column. We're going to talk a little bit about multi-column indexes in SQL Server and what they do and what they don't do. So last week I promised a longer video on parallel nested loops, and let me just tell you how many things have been just ganging up on me to prevent that from happening. One, Friday, when I went to actually record it, all of the lights in my office and actually apartment started getting weird and flickery, and like things were like turning off, like my computer monitors would start turning off and on, and then like randomly lights wouldn't work. And I don't know how many of you out there are certified electricians. I know that there are a lot of forklift operators in the crowd, but I'm not sure about the electrician segment of Darling Data fans. But if you ever open up a fuse box, like behind the panel, there are, well, and if you're in America, there are usually two big wires coming in. And they have screws that kind of hold the stuff in place to make a connection and provide electricity out through the fuse box and the apartment at large. And apparently just over time, because of the natural vibrations of the city of New York, the screws had come loose. And so they had to be tightened so that electricity could once again flow freely and smoothly throughout everything. So that got done like late Friday night, and by that point I was like, well, there's just no way in hell I'm trying to record a video about parallel nested loops now. I've already had a few drinks, and it's a dense enough set of explanations without the mind being a bit foggy. And so that didn't happen. And then, of course, the weekend came along, and you know what they say about weekends? No one watches SQL Server videos on weekends. No one cares. So, Monday kicked my butt. Lot of query tuning work done on Monday, and here we are on Tuesday. And I kind of realized that the material that I have is a bit too dense for just one quick video. So I'm gonna have to figure out a better way to present all that stuff. But it's in the works. In the meantime, I hope you'll accept this peace offering about multi-column indexes. So let's do it. All right, so I've got 4 queries here. 2 of them are using what Microsoft I don't know, hubristically refers to as the default cardinality estimator, which is stupid. It's just new. And 2 queries that are using the legacy cardinality estimator. And it's not legacy. It's just the older one. And what I want to show you here is, the first thing I want to show you here. This is first of many things that I'm going to show you here. And I'm going to try to make this one on the shorter side because it's hot, and part of the reason why it's hot is there's too much hair coating my head, in some places anyway. And it's a sweaty one here in the city, and I have not been maritally cleared to put the air conditioners in yet. So here we are, getting a little sweaty on camera for you. But what I want to show you first is that neither one of these cardinality estimators does a terribly good job of actually estimating cardinality. So here's what all 4 of these queries return. The first one, 269,420. I did not intentionally write a query that returned those numbers. I'm just now realizing what those numbers are now that I read them out loud. And then we have 2 that return 0. So let's recover smoothly from that. And let's look at the query plans, because what I want to show you in the query plans is how different cardinality estimation models handle these sort of predicates. Right? So we're just looking for first where creation date is less than close date, which actually, has rows that hit it, because often you have to create a question before you can close it. And then we have these, that make no sense because you can't close a question, or you can't create a question before you close, after you close it, something like that. So yeah, this just makes no sense. But SQL Server estimates the same number of rows for both of them. You get a same sort of stock guess of about 30% of the rows in the table. The post table has about 17 million rows in it. 5 million is apparently about 30% of 7 million. So we have that going for us, because 5 times 3 would be 15, and if we added 3%, then we would get like 99. That would bring us a little bit closer to, like, 5 point something million, a little higher. So trust me, math. We're good there. And the legacy cardinality estimator, the calculation is not nearly so straightforward, but the end result is that SQL Server thinks that 97,000 rows will qualify for this predicate, which is also wrong. It's a little bit less wrong, right? Because 269,000, it's a lot closer to 97,000 than it is to 5.1 million. But the legacy cardinality estimator does the same thing, and that's not exactly what I wanted. And it also gives you the same stock guess. Now, like I said, this math is a whole lot less straightforward to figure out. There's a lot of funny symbols and letters that are actually numbers and things like that. Basically, unless you are an advanced mathematician, it would do no good to try to explain this formula to you. You would never remember it anyway. It would do no good. So what a lot of people, notice I don't have any good indexes for these queries. We're just working off the clustered index. So let's take a first stab at an index for this query, right? Let's just say we want to create a query, we want to create an index on creation date and close date. All right, and so we'll get that index moving, and let's run these queries again. Now, the last set of 4 queries took about 7 seconds to run. They all generated parallel execution plans. We did some fancy, fun work. We got results back. Everything was groovy. And now with that index in place, well, I mean, do we really do any better? Not really. Everything finishes in just about the same amount of time. We get the same estimates for all of these, 97,318 here, 5.1 million, blah, blah, blah over here, and we get all the same results back. Now, the thing to keep in mind here is that multi-column indexes like this don't track any correlations between the columns in them. Right? You really only get a histogram on creation date. SQL Server may have in the background created a system statistic on close date. That's totally possible. But this isn't like a bad statistics thing. This is just SQL Server doesn't, like SQL Server indexes don't keep track of this. Right? It has no idea how many creation dates are less than or greater than close dates. Like, that's just not something that statistics track. And it's very, very hard to communicate some of these things to SQL Server. So, like, unless we had a check constraint that told SQL Server that creation date always has to be greater than close date, and that close date can never be greater, or creation date can never be greater than close date, creation date always has to be less than close date, then, we might get, giving a little bit more information might be kind of helpful, but SQL Server is going to have no idea how many creation dates will be less than close date, because remember, not every question gets closed, right? So close is going to have a lot of null values in it. So only the questions that get closed have values here. And SQL Server doesn't keep track of how many of those might just show up, right? We just don't have that kind of good information. So the only way to really give SQL Server any better, not the only way, but one way that you can give SQL Server a cleaner path to these sort of predicates is to use a computed column. Now, what I'm going to do is alter the post table, and I'm going to add this column, which converts a bit, converts these ones and zeros to bits. So when creation date is less than close date, it's a 1. When creation date is greater than close date, it's 0. And that's going to be that, right? So we add our computed column, and notice how quickly that added, because I did not add the persisted keyword. And I want you to pay attention to something else very closely here, is that I don't need to persist this column in order to create an index on it. Likewise, I also don't need to persist that column for it to get statistics generated on it. Persisted is just a special thing that you do when it's a tough choice to make because even persistent computed columns doesn't guarantee you a whole lot in the way of things going well when you query them. That's often quite a crapshoot. So that index is in place, and I'm just going to show a couple versions here with the I guess the default cardinality estimator. I'm going to go along with Microsoft's silly naming scheme, and we're going to just run these two queries. And these two queries finish a whole lot faster because we are able to very easily and quickly seek. And if this thing would just let me do the grabby thing and move the query up, we are able to very quickly jump to where the data that we care about, right? Notice that we didn't have to directly reference the computed column in the where clause. We just had to exactly write the form of the computed column in the where clause. But this is where we're looking for 1 equals this, and this is where we're looking for 0 equals this. And notice that cardinality estimates do improve quite a bit here because SQL Server has an absolute. I mean, SQL Server always thinks that one row is going to exist, even if no rows exist. You'll never see a 0. I mean, I'm not going to say never. You're almost guaranteed to never see 0 of 0 for one of these things, at least for like an actual data acquisition operator. There are probably some in-memory operators where you could see 0 of 0. But anyway, I digress. And in a minute, I'm going to undress because holy God, it's hot. But what you see here is that we get, because we actually stabilized that expression, we gave SQL Server an actual materialization of what we're looking for and what we care about. We are able to generate good statistics for exactly what we're looking for. So we get the exact 100% spot on guess here, and even though we get 0 of 1 here, that's pretty gosh darn close to it. We get very nice index seeks exactly to the data that we care about. We don't have to scan the whole index, figure out if 1 is greater or 1 is less, and it just saves a lot of time generally. So if you're dealing with query plans that even do something kind of simple, like you just want to figure out if one column is greater than the other, you might run into all sorts of issues with cardinality estimation. You might have a tough time indexing for those queries, and you might suffer all sorts of plan quality issues because you're not getting good cardinality estimates from these things. Remember, with the default cardinality estimator, you get a stock guess of 30%. That could be way off. With the legacy cardinality estimator, you get a very fancy math estimate, which in this case was closer to reality, but was still off by 100% or a little bit more, because it was 97 versus 269 420. Yes. Not going to jail for that. So if you find yourself having to do these sorts of calculations and you find yourself getting bad cardinality estimates and bad query plans, things slowing down, one option that you might want to look at is creating a computed column that expresses this stuff for you. Where this gets a little tougher is that I do run into a lot of people who have to make this comparison across tables. So let's just say, for the context of the Stack Overflow database, let's just say we were comparing a creation date column in the post table to a date column in users or comments or votes or something, or badges or any other column with a date in it. You can't really index that. You can't index across tables directly. You could create an indexed view and then create, if you needed to, create whatever other stuff you had to on top of that. But that would be one way of indexing across tables. Other than that, you would be looking at dumping stuff into a temp table where you combine the results and then index that, or just some other data materialization layer that is indexable in that way. Which, now that I think about it, realistically, it's going to be indexed views and temp tables, but all situational, isn't it? Anyway, I got other stuff to do, and there's some sort of aircraft going by. I hope doesn't pick up on the mic. But anyway, thank you for watching. I hope you enjoyed yourselves. I hope you learned something. I hope you are not hot and sweaty wherever you are. I hope that you are air conditioned and comfortable, and you're having a good day. If you like this video, I do enjoy a nice thumbs up, and I do enjoy a nice comment. Again, just go easy on me, because I'm having a sweaty one over here. If you like this sort of SQL Server content, please subscribe to the channel. You can join. No, let me refresh this so I get the exact number. You can join nearly 3,545 nearly other subscribers to get notified when I drop these precious gems. I drop these jewels on you. And I do also promise that eventually we will get to the parallel nested loops video, and I'm looking forward to seeing the watch metrics on that. I'm looking forward to see exactly how long viewers stick around for on that one, because like I said, it is some dense material, and it is kind of mind-numbing when you get down to it. But anyway, it's time for me to go de-sweat myself. So I'll leave you with that visual. Once again, thank you for watching. Goodbye. Why won't this thing stop recording? Oh wait, it did stop recording. No, it didn't stop recording.